Welcome to this lecture series in real analysis. We've previously seen that pointwise convergence of functions is not a strong enough notion to guarantee the continuity of the limit function provided the participating functions are continuous. But we saw via the uniform limit theorem that if you have uniform convergence of a sequence of continuous functions, then the limit function is indeed continuous. Today's lecture, we will talk about the relationship of convergence and differentiability. So if you have a sequence of differentiable functions converging pointwise, what can we say about the differentiability of the limit, and can you write down the derivative of the limit by taking the derivatives of the participating functions and so on? So that's the kind of the type of inquiry that we will indulge in. And one important result that we will use is the following lemma, which was the lemma about interchanging limits that we proved when we were discussing the uniform limit theorem. Right? So this was the lemma that immediately implied the uniform limit theorem. So it says that if you have a sequence of functions, we are not assuming continuity even, you have a sequence of functions which converges uniformly to some function f. And if we assume that for an accumulation point of s, so just fix some accumulation point of s. Note that this is not required to lie in S. It could be lying outside S. So fix an accumulation point of S and assume that all of these limits exist. Okay. Then the corresponding limit for the function f also exists, and you can calculate it by kind of interchanging limits. So this is a lemma that we will make use of. Okay, here is one problem for practice. And now let us get started. So here is our first lemma. Already it's a very nice lemma, but I have termed it as a preparatory lemma because we will strengthen it in the next page. So fix a sequence of differentiable functions. Assume that the sequence converges pointwise to a function f. Now, if the derivatives, since these are differentiable functions, we can talk about their derivatives. If the derivatives converge uniformly, then the limit of the derivatives is the derivative of the limit. Right? So one way to express this as is that limit of the derivatives is derivative of the limit. In this kind of equality we definitely wanted. It's just that we need some hypothesis to have this equality. Okay, and we will strengthen this, whatever this lemma is saying, we will prove a stronger lemma soon, but for the moment, this is what we have. Yeah, so how do we do this? Give me a second. Yeah, so fix a point in the domain and define for each n the function phi n as phi n of t is this ratio. All right, and also define phi as, forget it. So we define it as, so x is fixed. X is a fixed point. For each t here, we define phi n t as this ratio and phi t as this ratio. Not very mysterious as to where these definitions are coming from. Clearly, maybe I'll make a note on the side. So note that phi n's converge pointwise to phi. And that's clear because fn converges pointwise to f. So that's clear. Okay. Also, this limit is equal to the derivative of fn at x. That's almost, we talked about derivatives and I don't want to say anything. Each fn is differentiable, so the limit of phi t as t approaches x is the derivative of fn. Fine. So what we will do is, we will show that this convergence is actually uniform. Okay, and then use the lemma about interchanging limits. That's it. That will prove what we want to prove. So what we want to prove is that, first of all, that f is differentiable at x, which will be same as trying to show that the limit of this thing as t approaches x is existing. So that will show the differentiability of f at x, and showing that the derivative of f at x is same as the limit of these numbers. So that will be done in one shot once we show that this convergence is uniform, and we will just invoke the lemma about interchanging limits that we recalled in the beginning. Okay, so how do we show uniform convergence of these of phi into phi? So fix 2 points. Fix m and n. We will use Cauchy's criterion. So let m and n be fixed. So then let's estimate this. This is, by definition, right? That's what it is. I guess this line is not horizontal. Maybe now it is. I don't know. Yeah. So we have that. But this is equal to... So what did we do? We just did some basic algebra. We pulled it to this side and that guy to that side. Yeah. Yeah, I don't think there is any mistake. The signs are all right. Yeah, all the signs are fine. Yeah, so this is what it is. But this we can also write as the difference function, the function that arises by taking the difference of fm and fn evaluated at t minus this thing evaluated at x divided by t minus x. Right, because this number is just same as this number, just a change of notation. And this number is same as that number. Okay, great. But note that this function is a differentiable function. Why? Because it is the difference of two differentiable functions. So it is a differentiable function, and hence by mean value theorem, this is equal to that for some p, of course absolute values, for some p in the open interval containing t and x. So I'll just write it like this. Of course, t could be greater than x, then this would be meaningless, but then you'll have to switch the order. So yeah, I don't want to fuss too much about that. Okay, so we have this. I don't know if I have enough space. Okay, fine. So therefore, this is at most the supremum. Right? This term is equal to that term for some p. So we can write this inequality. But now, by hypothesis, we knew that the derivatives, the fn primes is a sequence, is a uniformly convergent sequence. So if m and n were large enough by Cauchy criterion, this would be estimated by epsilon. So if I will be a little bit informal here, so if so fix an epsilon greater than 0, then for m and n large enough, we know that the right hand side, we know that this supremum is less than epsilon, and therefore the same thing can be said about this difference. So thus, if m and n are large enough, we have this is less than epsilon for all t. For all t in the domain, of course, the domain here is this set. And therefore, the uniform convergence holds. So thus, by Cauchy criterion, this converges uniformly. So this is a uniformly convergent sequence. It is uniformly convergent. And of course, it converges to its pointwise limit. Its pointwise limit was phi, and so is uniformly convergent to the function phi. In fact, now just use the lemma about interchanging limits. So by interchanging limits, this we recalled in the beginning, we know that limit t tends to x, limit n tends to infinity, phi and t. So since x is an accumulation point of the domain, we can do this. The interchanging limits lemma asks us to use an accumulation point of the domains of the function. So we are using that. So this limit is equal to that. But what is the left side? The left side is this expression, right? Because this limit is precisely that. This limit is nothing but phi t. Phi t is that. And the right side is because this limit is the derivative of, sorry, what have I written? This limit is the derivative of f n at x. So therefore, this what we have done proves that this limit exists and is equal to the limit of the derivatives. So the two things have been proven in one shot. So proof is nice, proof is interesting, but the result is more important for us. And of course, the proof is very nice. So once again, if you have a pointwise convergent sequence of differentiable functions whose derivatives converge uniformly, then the limit of the derivatives is the derivative of the limit. So this is our preparatory lemma, and now we will strengthen it, and that will be it. So here is the main theorem. Again, we assume that we have a sequence of differentiable functions. And this time, we are not assuming that this sequence is a pointwise convergent sequence. We are only assuming that there is a point in the domain such that the corresponding sequence of real numbers that you obtain is convergent. So this sequence of functions produces this sequence of real numbers once you choose a point in the domain. We are assuming that there is at least one point in the domain for which the corresponding sequence of real numbers is convergent. Much, much weaker than assuming that this being pointwise convergent. However, further, if we assume that the sequence of derivatives, or since each fn was differentiable, we can create this sequence of derivative functions. If this converges uniformly, then we would like to prove that, very interestingly, that the given sequence of functions is actually uniformly convergent. Not only pointwise convergent, but uniformly convergent. So this actually strengthens the previous proposition quite a bit. And then the second conclusion is the same as what we had in the previous lemma, that the limiting function is differentiable and the derivative of the limit is the limit of the derivatives. So 1 implies 2 is immediate from the previous proposition. This is from the previous proposition. And that is an exercise, if you will. So what we want to understand is why should the uniform convergence of the functions follow from the given hypothesis. And the way I would like to do it is just illustrate the main idea and then let you read the full proof, which I will show. So here is the main idea of the proof. It's basically Cauchy's, it's mean value theorem is at the heart of the main idea. So what we have is, we want to show uniform convergence of these functions. So fix any point in the domain. And suppose we have natural numbers m and n. Then, to show uniform convergence by Cauchy's criterion, what do we want to do? We want to estimate this difference. Right? We want to estimate this difference and show that if m and n are sufficiently large, then regardless of the value of x, this can be approximated by epsilon. So since I'm only illustrating the main idea, I'm not writing the formal details. So how do we estimate this is the point? And the way to estimate, or the one way to estimate, is the following. Just write this as so we write it like this, but of course this is not correct. We have to add it back. So all we did was that we subtracted this term and then added it back so that equality is maintained. But now we can apply triangle inequality. So again, recall this x0 is the special point for which this sequence is convergent. So by triangle inequality, this is at most right, straightforward triangle inequality. And now we will shuffle this thing around. Let me do it here because I don't have much space. So this term will go that side. So basically I will be collecting, what do I want to do? No, I think it's fine this way. We don't need to shuffle around anything. I'll just write this as follows. Okay. All I've done is say that this is equal to that, which is of course true, and this is equal to that. But now by mean value theorem, since this is a differentiable function being the difference of two differentiable functions, by mean value theorem, more precisely by Lagrange mean value theorem, this is equal to the derivative of the difference at some point, I'll write t, multiplied by x minus x0, where t is some point between x and x0, immediately by Lagrange. However, this is at most b minus a. X and x0 are within the enclosed interval a comma b. So their difference is at most b minus a. So I will write an inequality here and write b minus a. Okay, I hope that much was clear. And instead of writing it this way, let me write it like this. Fm prime t minus Fn prime t. I hope no confusion was caused. And now, here is the point. Since we had assumed uniform convergence of the derivatives, if m and n are sufficiently large, you can estimate this by whatever you want. You can make this as small as you want, regardless of the t you have here. This is of course some fixed number. So the point is, if m and n are sufficiently large, this is smaller than whatever you want. And same, if m and n are sufficiently large, this is also smaller than whatever you want because of this technical sort of assumption. So the right side you can make as small as you want if m and n are chosen sufficiently large, and this estimate doesn't depend on the choice of x. So this can be made as small as you want if m and n are sufficiently large. And now, by Cauchy's criterion of uniform convergence, we see that the sequence is uniformly, this sequence of functions is uniformly convergent. That's it. That is the heart of the proof. But here is the formal, the full formalize. Yeah, so that proves the main thing. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.